Hey everyone. All right, let's break down one of the most important chapters you're going to cover in your engineering studies. Chapter 11. We're talking about how we design buildings that can actually survive the incredible force of an earthquake. And look, this is about more than just passing a test. This is about understanding the science that literally saves people's lives.
So, if you're working from this building technology textbook, you already know Chapter 11 is a big one. Our job today is to unpack it for you, to pull out the core ideas and make them really stick. The goal? For you to walk into your exam feeling totally prepared.
You know, this is really the fundamental question behind everything, isn't it? How can a static, unmoving building possibly stand up to something as powerful and unpredictable as the ground shaking beneath it? Well, the answer is a mix of really smart design, material science, and some serious testing. And we're about to get into all of it.
So here's our game plan. We're going to start with the basics of what it means to survive the shake. Then we'll dive into building strong from scratch and upgrading older buildings. After that, we'll look at how we even know if they're safe, and we'll wrap it all up with a focus on how to nail your exam. Let's do it.
First things first, let's get the big picture. Chapter 11 is all about giving you the engineering toolkit you need to design and reinforce buildings against seismic forces. It's about being proactive, right? Making sure a building is ready before the ground starts moving. And just so you know, we're sticking right to the book. No detours. This whole explainer is designed to perfectly mirror your textbook, walking you right through sections 11.1, 11.2, and 11.3. You could think of this as your personal guide through the chapter. Okay, our first main topic, covered in section 11.1, is all about starting fresh. When you have a clean slate, a new project, what are the absolutely critical choices you have to make to build earthquake resistance in from day one? And really, everything in this section boils down to one thing: seismic safety. Now, this isn't just some vague concept. We're talking about very specific choices. Things like the building's shape, the materials you use for strength and flexibility, and the structural systems you design to absorb all that energy.
The textbook splits this up into two main areas you gotta know. First, you've got the general factors that apply to any building, stuff like analyzing the ground conditions, but then it gets into the unique problems with tall buildings. You know, how to handle all that sway, design super deep foundations, or even use base isolation to literally disconnect the building from the ground's movement. You need to get both parts.
So designing a safe building from scratch is one thing, but what do we do about the millions of older buildings that were put up long before we had these modern seismic codes? Well, that's exactly what section 11.2 on retrofitting is all about. So what exactly is retrofitting? The slide nails it. It's all about strengthening a building that's already standing. It's basically a massive structural upgrade, reinforcing an old design to handle forces it was never, ever intended to face. The chapter breaks this down into two really practical buckets: the how and the what with. It goes into the different techniques engineers can use, like adding external bracing or brand new shear walls, and then it covers the amazing materials that make it all happen, like fiber-reinforced polymers.
Okay, so you've designed your new building, or you've retrofitted an old one. How do you actually know it's safe? How do you prove your calculations are right? That's the whole point of the last section we're covering, 11.3, Verification Methods.
The book lays out two main ways to do this. First, you have destructive tests. And yeah, it's exactly what it sounds like. You take a component and you literally break it to find its absolute limit. It's the ultimate stress test. The other way is non-destructive testing, or NDT. This is more like giving the building a checkup, using things like ultrasound to find hidden problems without leaving a scratch. All right, we've gotten through the core material. Now let's get down to business. How do you take all this and turn it into a fantastic grade on your exam? Let's zero in on the key takeaways you absolutely have to know. When you're studying, just lock in on these three steps. First, really master all the design factors for new buildings from 11.1. Second, get a solid handle on the retrofitting techniques in 11.2. And third, make sure you can clearly explain the difference between the testing methods from 11.3. Just think, new buildings, old buildings, and proving it works. That is the heart of this chapter. And here's a pro tip for you, straight out of the textbook itself. Seriously. Open your book and flip to page 230. The authors actually put in an exam question solution section. This is pure gold. It shows you the exact kind of questions they'll ask and how to answer them. Whatever you do, don't skip this part. I want to leave you with this one last thought, because it really gets to the heart of what this is all about. No building is earthquake-proof. That's not the goal.
The real mission isn't to prevent a single crack, it's to prevent a total collapse. It's about designing buildings that bend but don't break, giving people the precious time they need to get out safely. That's what seismic engineering is all about.
So as you go back and study this, think about this question. Which of these three areas is the biggest engineering puzzle right now? Is it designing brand new cutting-edge buildings? Is it the massive challenge of retrofitting our old cities? Or is it coming up with even better ways to test for safety? It's a huge question, and it's one that engineers like you are going to have to solve.